So here we have a differential equation. Now, is this singular or regular? Singular or ordinary? Is this a singular differential equation or ordinary differential equation? At x equal to 0, what happens?
0.
This vanishes, right? So if you, for example, if you divide it by 3x, then x equal to 0 is a singular point, right? Is that right? If you divide by 3x, you get a fraction where the denominator gives you 0 at x equals to 0. So x equals 0 is a singular point. Okay? Now, you are taught that if x equal to 0 is singular, what kind of solution are you supposed to find? Frobenius. You have to use the Frobenius type solution, right? However, there are cases where you want to find the solution for power series around 1 rather than 0. So we learned there's something called the Taylor series centered at x equal to a, or power series centered at x equals to a. So if a is 0, then it's just a regular power series, a n x to the n, right? But if you have a as something other than 0, then it's a power series centered at some other point. Now, why would you want to do that? Well, see, if you knew the power series and Taylor series well, then I don't have to explain all this. But since it's been a while and you probably didn't really understand it that well, let me stop this for a while and let me digress and try to explain to you this business of having a power series around some other point other than 0. Okay, so here's what you do. Suppose you wanted sine of 1. Okay. And so you're trapped in an island, and you know the story where you don't have a calculator and you have to make your own sine table or something. How do I do that, right?
Like Castaway.
Yeah, like Castaway. Yeah. And just for some reason you needed sine of 1. What would you do? Well, if you are a mathematician like me, I would first think about sine of x's Taylor series. X minus 1 over 3 factorial, x plus 1 over 5 factorial, this is cubed, x to the 5th, minus 1 over 7 factorial, x to the 7th, so on and so on. And sine of 1 would mean it's 1 minus 1 over 3 factorial is 6 times 1. 5 factorial is, what's 5 factorial? 24 times 120. 120. And minus, I remember this 5040, I think.
Yeah.
And then times 1. Okay, I'll delete 1. So if you plug in 1, it's just 1, so you get that. And as you can see already, this is pretty small, so it's not going to vary that much, right? So I can just say it's about 5/6 and a little bit more. What's 5/6? It's like 1/6 is 0.1666, so 0.85. Okay, that's my guess. Does anyone have a calculator?
0.83.
Huh?
0.83.
Ah, okay, so I'm off. So my guess was this is 0.85, and your calculator told me it's 0.83, right? So, I mean, if I took some time to actually calculate it, I would get it, right? So that's how you make use of the Taylor series. Right? Now, the thing is, if you wanted something other than 1, say for 2, now here's where the trouble happens. You have to put 2 cubed, 2 to the 5th, 2 to the 7th, and let's see, that's 8 over 6. So I mean, that's 1 point something. That's pretty huge. This is 32 over 120. That's not too small, right? So what you see is that the further away you're from the 0, you end up having to calculate more and more terms. Okay? You see my point? If you're trying to use this to find, for example, sine of 0.1, that's super easy. You just plug in 0.1. Already 0.1 to the cubed is like 0.001 times 1/6, so that's very, very small. So you already know that sine of 0.1 is very small, similar to 0.1. That's not a problem. But once you have some number that's further away from 0, it's like 2 or 3 or 4, it gets bigger and bigger, then you can't just be satisfied with a few terms. You actually have to go further. Okay? And it could be like 1,000 terms, million terms, depending on how accurate you want your approximation to be. Okay? So in that case, rather than trying to use 2 into here, it's probably better to find another power series for it, and that's called the Taylor series. So here's what Taylor did. You don't always have to expand it in terms of x to some power. Why not make sine of x equal to, say, what do I want? Sine of x for a0 plus a1 x minus, say, pi over 2. Because pi over 2 is about 1.5. It's pretty close to 2, right? So if I can figure out these values for x minus pi over 2, then that could be better. Okay, so I can rewrite sine of x as an infinite polynomial with powers of x minus pi over 2. And then if you do this, and then figure out what a0 is, what a1 is, what a2 is, then you can use this to calculate this better, because now when you plug in 2 minus 1.5 is about 0.5, so this plus 0.5 times this, and 0.5 squared is 1/4. You can make a calculation like that. Okay, so actually let's do it. Okay, all right. So first, how do you find a0? How would you find a0?
When x equals 0?
Huh?
X equals 0?
No, if you put x equal to 0, this doesn't die out. It's negative pi over 2 times a1. This squared times a2, so that's not good. How can you find a0 here?
X equals pi over
X
2.
equals to pi over 2. If you plug in x equals to pi over 2, sine pi over 2 will be your a0, because everything else, if you plug in pi over 2, it goes away. Right? So what is a0 then? Sine pi over 2 is 1, isn't it? Yeah. So that gives you a0 as 1. Okay. Now, what sine? How would you find a1? What's the idea for finding a1? You differentiate both sides, right? So cosine x. This will go away. This will be a1 by itself. This will be 2a2 x minus pi over 2. 3a3 x minus pi over 2 squared, and so on, right? Now how would you get a1? Plug in pi over 2. Right? Plug in pi over 2. Cosine pi over 2 is 0, so 0 equals to a1. Now how would you get a2 then? Differentiate again, and you plug in. So a2 will be, differentiating cosine gives you negative sine. Negative sine of pi over 2 is negative 1. So a2 is?
Negative 1.
No. a2 is?
Negative 1/3.
Negative 4.
What?
You were close, but other people are not.
Negative 2?
Huh? Huh?
Is it
Can we do it?
How is it not negative 1/3? Oh, A2.
We're doing A2.
2/4.
Huh?
2/4.
How? Okay, I agree with you, but how did you get that?
Negative 1/2.
Negative 1/2 should be the better one. Okay, so I mean 2/4 is 1/2, but it should be negative 1/2. Okay, how? Differentiating cosine x gives you negative sine. Negative sine of pi over 2 is negative 1, but negative 1 is equal to the right side. What would you get on the right side if you differentiate? Would you get A2 as the first one? What would you get as the first term?
2.
2A2 will be the very first term, right? Because this goes away when you differentiate. Isn't that right? Okay. So if you differentiate, 2A2 is what you get on the right side. You get negative 1. So A2 will be negative 1/2. Okay. If you go on, this will be 0. The next one will be, let's see, 4 times 3 times 2, which is 24. And that will again be positive. So A4 will be 1 over 24. Okay, so here's what you get. You get this as 1. This will go away. That will be 0. This will be negative 1/2. This will go away. And this one will be plus 1 over 24. And then we're almost there. Now, in order to get a sine of 2, I said 2 minus, this is about 0.5. 1/4. 1/4 times 1/2, that's 1/8, or 0.125. So 1 minus 125 is 0.8877 something. Okay, so I think that's, what did you get? What's the actual value? 88? 0.88? What side of 2, please?
0.909.
Huh?
0.91.
0.91? That's a lot.
Sine of 2.
Yeah, sine of 2.
Yeah, 0.909.
0.91? Okay, so then I'm way off. Maybe I should really have done
Is
3.1.
radians and degrees better?
No, I'm talking about here radians. It's in radian mode, right?
Mhm.
Yeah, okay, so in radian mode, this should be, I just did it in my head, but it should be more than that. Okay, so probably,
Still
one
pretty
thing is
close.
that I just rounded pi is 3, which I shouldn't be. It's 3.14 is what I should have done. And there's something more here, so I should have added that too. So after that, I should have gotten 0.91. Okay. So does that kind of explain why you want a power series centered at other places, right? Okay, so that's what we were trying to do. Now, here, there's another reason why you want to do a power series centered at other point. Your initial condition is at 1, right? Now, we saw a moment ago that if your initial condition is at 0, then that gives you the A0 and A1 of your power series, right? Here, that's no longer true, okay? And in order to get the very first two, A0 and A1, nailed down to fixed value, it's better to have this as A n x minus 1. So that's what we're going to do. So we'll try to solve that for y equals to this thing, okay? All right, so let's differentiate that twice and plug it in here. So what do you get? 3x sigma n from 2 if you differentiate twice. N times n minus 1 times a n x minus 1 to the n minus 2 plus 5 times sigma n from 0 to infinity of a n x minus 1 to the n time. That has to equal to 0. So that's what you get if you plug in that thing. By the way, these things when you write it like this and you plug it in, those are called Ansatz. Ansatz. It's a German word for sentence. Okay, so as I explained, we're basically doing guesswork, educated guesswork to find solutions, right? And one of the ways to find the educated guess solution is to think about, if you cook up a possible form of the solution, and you plug it in there, and that's called the ansatz. Okay. All right. So we want to now expand it, but here lies another problem. Before, we were able to write it as we were able to bring this x inside and increase this exponent, right? Now what do you see? It's different. You can't do that anymore, right? So what should we do? Do you have any idea? I guess this will be a little hard for you to think. The idea is this. You write it as 3 times x minus 1 plus 1. Plus, this is the same. I'm just being lazy here. So write it like this. And then you multiply this separately. Okay?
Wait, what'd you just do? What's x?
X is x minus 1 plus 1, isn't that right? If you have x minus 1 plus 1, what's it get?
X.
X. Yeah, so I'm just rewriting x as x minus 1 plus 1. Why would I want to do that? That's because x minus 1, when you multiply to here, it increases the exponent. And that's exactly what we need to do, right? So because now instead of organizing in the powers of x, we want to organize it in powers of x minus 1 to some power, okay? So that's why this was needed, okay? All right, now we multiply them and we get the following. Sigma n equals to 2 to infinity, 3 times this thing, so it's 3n, n minus 1, an. And because when you multiply this to that, it increases the exponent, this will become n minus 1. Whereas there's another one which is 3 times 1 times this thing, which doesn't increase any of the exponent. So it will become just n minus 3n, n minus 1, an, x minus 1 to the n minus 1. How much time do I have left on the recording?
12 minutes.
Huh?
12
minutes. Very, very good. Okay. All right. So here, and then we have the final one, sigma n equals to 0 to infinity of 5 an x minus 1 to the nth power. Yes. Oh, this should be n minus 2.
Yeah.
Right? Yeah. Thank you. All right. So I have n minus 1, n minus 2, n. Oh no, none of them match. So we need to shift everything. Okay. Let's shift this and this. Okay. So that everything matches with x minus 1 to the nth power. Okay. So we'll shift this and this. So this one you have to shift n as n should be replaced by n plus 1. For this one you should replace n by n plus 2 to make this into n and n. So that gives you sigma n from what? N plus 1 equals to 2. If you solve for n, you get
0.
n plus 1 equals to 2. If you solve for n, you get 1. Okay? So 3 n plus 1 times n, a n plus 1, and x minus 1 to the nth power. And then this one, sigma n plus 2 equals to 2. Solving for n, it gives you 0, infinity, 3 n plus 2, n plus 1, a n plus 2, and then x minus 1 to the nth power. Plus this we don't touch, it's the same thing as before. Okay. All right. So we did all this work. Let's see where it leads us to. Okay, now n equals to 0 gives you what? This doesn't produce anything. That one gives you 6 times, if n is 0, this is 3 times 2 times 1, so that's 6 a2 and x minus 1 to the 0th power plus 5a0. 5a0, x minus 1 to the 0th power. That's what you get. And then starting from 1 and afterwards, everything starts producing terms. So we have sigma n equals to 1 and afterwards. And let's see, it's a huge sum. 3 n plus 1 times n, a n plus 1 plus 3 n plus 2 times n plus 1 times a n plus 2 and 5 a n times x to the x minus 1 to the nth power. They all have x equal to 0. And
That's
then-
it. Just the top
Yeah.
one above it's n equals 0.
Yeah, this one is when n is equal to 0, this one is 1 and afterwards. Okay? So that tells us that 6a2 plus 5a0 is 0, which gives you that a2 is negative 5 over 6a0. That's 1. But after that, you end up having this two-term recurrence relation. So you should solve this for the highest order, highest term. So 3 n plus 2 n plus 1 a n plus 2 is, if you move this to the other side, it's negative 3 n plus 1 n a n plus 1 minus 5 a n, and then dividing everything by 3 n plus 2 n plus 1 both sides. That will be the recurrence relation. That's going to be the recurrence relation. All right. Now, what is A0 here?
2.
A0 will be 2. A1 will be negative 3. That's because if you write out what that y is A0 plus A1. It's centered at x minus 1. It's centered at 1, so it's x minus 1. A2, x minus 1 squared, and so on and so on. So if you plug in 0, if you plug in 1, both sides, everything vanishes except A0, right? So A0 must be 2. In the same way, if you differentiate it, you get A1 plus 2A2 x minus 1, and then plus something. They all will have x minus 1 there, so if you plug in 1, everything will vanish and you're going to get A1 for y prime of 1. But what is y prime of 1? That's negative 3, right? So you already know that A0 is 2, A1 is negative 3, and this one says that A2 is negative 5 over 6A0, which is negative 5 over 3. And then this one tells us that A3 is negative 6A2 minus 5A1 over, see, I'm putting n equals to 1 here, so it's 6 times 3, 18. And then you plug in these values, A2, A1, so negative 6 times that's positive 10. A1 is negative 3, so plus 15 over 18, so it's 25 over 18. And I'm getting tired, so let's just write down only the first 4 non-zero terms, okay? So what's the solution? 2 minus 3x minus 1 minus 5 over 3 x minus 1 squared plus 25 over 18 x minus 1 cubed plus da 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 da. Okay, so that will be your solution.